Okay, so I think we'll go ahead and get started. Today we're going to hear from Dr. Liviu Mirica, and he's going to talk to us about the magic of catalysis. He received his PhD in chemistry from Stanford in 2005 and is currently an associate professor in the Department of Chemistry at WashU and is a member of the International Center for Advanced Renewable Energy and Sustainability. His research is very diverse and includes developing catalysts for making high-energy liquid fuels from methane and generating hydrogen fuel. So, he seems to be the best person then to tell us more about this in his talk, Greenhouse Gases to Liquid Fuels, the Magic of Catalysis.
Thank you very much. Thank you very much, Caitlin, for the very generous introduction. Let me see, I need to turn this on. Is it good? Yes? Okay. Make sure I'm not going to be running late. I have my phone here. So it is a pleasure to come here today and tell you a bit about what we'd like to do as a chemistry research group. But before I'll do that, before I'll present to you some of our research interests, I will be focusing on the general aspect of why this thing called catalysis is important for our society, and how can chemists, such as myself and others present here, could help addressing some very important problems that our society is facing today. And I'll be talking about trying to address the energy problem or soon-to-be crisis in terms of how can we come up with new sources of energy, especially renewable energy sources. So really that's what I'll be doing, and I'll be introducing catalysis as a way of trying to help address that problem. So I'll start with a very simple graph I have shown here. And maybe throughout the presentation today, I'll be asking some questions in the audience, so please feel free to answer some of those questions. But what I have here, I'm showing you where do we get our energy? Where does our society get the energy for using it either in our cars or using it to power the electricity that we have in our house and many other requirements of energy. So what I'm showing here is the amount of energy the entire society, our entire planet requires per year. And this is shown a number from 2001. And these units, terawatts, represent how much energy. It's a unit of power and represents how much energy we are using or we were using in 2001. And then where is that energy coming from? So different sections of this bar graph here represent the percentage of the source of that energy. For example, most of it you see comes from oil, and I'm sure most of you are aware of that. Also, we're still using quite a large amount of coal, and we use power plants that use coal to provide energy. At the same time, we use natural gas, the component of which, the main component will be methane, and we'll be talking about that in a bit more detail in a few slides. But you see, most of our energy comes from these, what I'm calling classical sources of energy. These are also called fossil fuels, because they represent, they're found in Earth's crust, and we are extracting all of these types of fossil fuels, which provide most of our energy. So if we take into account our society, the population of Earth, and how would those numbers increase, and how would our requirement or requirement for energy would increase, people have different approaches, and people have calculated how much more energy are we going to need, let's say, in 2050. So if you look at this, we may actually need to double the amount of energy, or we'll be likely doubling the amount of energy we will require. Maybe because also population increases very fast. Also, we're consuming more and more energy per capita. So in this case, what we have here, for example, is expected that we may need up to 28 of these units, terawatts, by 2050. So that's at least twice the amount of energy we will require in the next 30 to 40 years. So the big question is, where can we come up with these additional energy sources? Anybody has some idea about that?
Recycle.
We could try to recycle. That's a great point. That's kind of what I tried to get at in my presentation. You could imagine that maybe, how about if we just use more coal, more gas, and more oil? Could we maybe make up this difference, or could we be able to provide that additional energy? The short answer is maybe we could do it in a very short term, but in the long term, that will not be too feasible. First of all, because the sources of these fossil fuels, they're not infinite. At some point, we'll be running out of these fossil fuels. So that's one of the problems. Another problem, which is actually very important, is related to the effect of the use of these fossil fuels on our environment. I'm sure you heard of things such as global warming, as well as greenhouse gases. So usually when you use these fossil fuels, you end up making a gas it's called carbon dioxide. Or also I'm going to call it CO2. That's the chemical formula of carbon dioxide. And when you burn these fossil fuels, gas, coal, or oil, you end up releasing carbon dioxide in the atmosphere. So it turns out that the levels of carbon dioxide in the atmosphere have been increasing for the past hundreds of thousands of years. So they're much lower levels before our society has begun to use more and more of these fuels. So the most dramatic increases in the use of fossil fuels has occurred in the past 100 to maybe 150 years. So this is the biggest problem of using these fossil fuels. The increase of carbon dioxide levels in the atmosphere, which leads to the increase of global warming. Because carbon dioxide is a very efficient greenhouse gas, it sort of keeps the heat inside the atmosphere of our planet. So that's actually why having more and more levels of this carbon dioxide in the atmosphere is definitely not a good thing. In addition, we're going to be running fairly soon out of these fossil fuels. So the big question is then, how can we come up with this additional energy? And it was being answered from the audience. The answer from the audience addressed or mentioned the possibility of trying to recycle or try to use renewable energy resources, trying to use some source that will allow us to keep using that source and not, in this case, create, for example, more carbon dioxide, but also have a larger amount of energy resource available. So that's exactly what people are trying to address. Both scientists and engineers are trying to develop, first of all, the use of new or renewable energy sources, but also try to use energy sources which are not involving these fossil fuels. Because if you're going to use a fossil fuel, they're usually carbon-based. They have carbon atoms in them. Therefore, they end up making carbon dioxide. So trying to use some sources which are not, we're going to call them carbon neutral energy sources, that will allow us to maybe address this kind of a problem. It turns out one of these sources, I'll mention that in a couple of slides, will be solar energy. Try to take advantage of the sunlight, and try to convert that into accessible energy. And one way of doing that is trying to convert our solar energy store it into some form that could be useful. For example, if we could take solar energy and make some kind of a liquid fuel that we could potentially use it in our car, that will allow us to maybe bypass the use of these fossil fuels. So I'm going to be addressing some of the chemical processes that I would like to tackle, which will be related to these energy processes. So let me just show you here one picture, and actually I'm going to address some of the chemistry and the engineering behind this. This is a hydrogen fuel cell car. There are quite a few examples of these prototypes of hydrogen fuel cell cars. They use hydrogen as their fuel. I'm going to show you here, maybe it's a bit more complicated, but just imagine that instead of having gas or gasoline or diesel as your liquid fuel, you're going to have hydrogen. Hydrogen, it's a gas. However, you can compress it such that you can have the similar type of a tank, maybe slightly more specialized tank in your car, and have hydrogen instead of gasoline. That's exactly how this car works. And what happens in this engine, in this fuel cell, you take hydrogen and combine it with dioxygen or oxygen, which is found into our atmosphere. And the chemical reaction is shown here. How many of you have seen this reaction before? No? No? Okay. So this is a very simple reaction. if you have taken, or if you'll take soon general chemistry, you'll see that this is maybe one of the first reactions you're going to look at in this in your first chemistry course. This is because this reaction is very simple. It takes hydrogen gas, oxygen gas, and makes water. Water, of course, is a very benign chemical, right? You can drink it. Actually, this will make a very clean, very pure water. So this will be a very nice use of a fuel which is not based on carbon atoms, therefore it's carbon neutral or carbon free. You react it with dioxygen, which is present in the atmosphere, and the only product you make is water. In this case, most likely there will be water vapors. There will be water vapors coming out of your tailpipe and in your car. So of course, this will be a very environmentally friendly type of a car or of an engine. And this actually, for those that maybe have taken chemistry before, this is a very thermodynamically favorable reaction. This reaction wants to proceed. This reaction does proceed without any input of energy. Now, there is a small caveat. You may say, we've solved the problem. Let's just all buy hydrogen fuel cell cars, and we're going to use hydrogen as our fuel. Well, it turns out that the hydrogen they are making nowadays for testing and showing that you can use such a car is actually made from fossil fuels. They take oil, they convert it chemically in these huge power plants, and they make hydrogen. But while they make hydrogen, which is very clean, they also make carbon dioxide. So even though this car itself has a very clean engine, it has a very clean chemical process that runs this car, in order to make hydrogen is, in this case, we're using still fossil fuels. So the big problem that chemists and engineers and scientists in general are trying to address is, how can we produce hydrogen cleanly? So that will be pretty much one way in which people are trying to now use solar energy and try to make hydrogen gas, make this clean fuel by using a renewable energy source and very abundant energy source, solar energy, which is by far the most abundant source of such renewable energy. So it turns out, how can you do that? Well, we could actually try to run this reaction in reverse. So I mentioned the reaction as I draw it on this slide going forward is very favorable. If you want to go in reverse, you need to input energy to make that reaction go in reverse. In that case, we're going to have some energy to input some energy. In that case, we'll be using solar energy. So the way people are trying to address that, and again, maybe this is a bit of a complicated slide, but now we're trying to do exactly the opposite. Let's take water and split water into its two components, hydrogen and oxygen. Let me show you here. I have the reaction. So it's exactly the reaction you show on the previous slide, but since now this will be unfavorable from an energetic point of view, we'll have to put in some additional energy, that is solar energy, to allow the splitting of water into hydrogen and oxygen. This may seem simple, but actually it's quite complicated. This is one approach, sort of a combination of chemical and engineering approach in trying to use solar energy, or use sunlight, use sort of what's called a photovoltaic assembly. I'm going to make that simple to it. It's almost like in your solar-powered calculator, you have that small photovoltaic cell, that small solar battery that runs on light. So if you can try to make slightly more evolved versions of those solar batteries, you could actually help to split water into hydrogen and oxygen. Now, it turns out this process is, even though it seems simple, it's quite difficult because you have to deal with two different parts of this reaction. We're going to call those half reactions. And I've shown them here. You're trying to make hydrogen gas, and then you're also trying to make oxygen gas. And the two reactions occur at the two ends of this so-called solar fuel cell, sort of the reverse of the fuel cell we saw on the previous slide. So trying to put in water, which of course is very abundant on Earth. So trying to put in water, solar energy, which is free. And then we make oxygen, which could be released into the atmosphere, and hydrogen gas, which can be stored, and could be used that as our fuel in that hydrogen fuel cell car that I showed you on the previous slide. So by you taking advantage of this reaction, the splitting of water, the water splitting reaction, we can actually make hydrogen gas much more cleanly, much more environmentally friendly. Therefore, we don't have to use fossil fuels anymore to make a clean energy, a clean fuel. And then we could take our hydrogen that we made in this process, store it into a tank, store it into our car, and then run our hydrogen fuel cell car, which now indeed the overall process is completely carbon-free, and it does take advantage of a very inexpensive energy source, solar energy. So these are some ways in which chemists are trying to address, or chemists are trying to help these processes, or trying to help addressing these problems. The way we tend to try to address those problems is playing with this thing, which I listed above the arrow. Okay, I abbreviate it as CAT. But what does that mean? Well, it turns out what does that mean is going to be a catalyst. And that's what we're going to be talking about in a few slides. Let me show you another application of catalysis before we're going to go and talk about catalysis and catalysts. Let me show you another, show you here greenhouse gas, again, carbon dioxide. In addition to trying to limit the amount of carbon dioxide we put into the atmosphere by using fossil fuels, we could also try to address whether or not we could take some of the carbon dioxide which exists in the atmosphere right now and try to convert it into something useful. That could be useful chemicals. It could actually be some form of a fuel. So that's another chemical process that we could try to address by developing these catalysts, which I'll be talking to you in a few slides. So one type of reaction that we're trying to address, and I'm not going to spend too much time on how we're trying to do that. I won't be talking about our approaches in this particular reaction. But this will be taking carbon dioxide, this greenhouse gas, and convert it, in this case, to a chemical that's called methanol. Okay? Methanol, this is the chemical formula for methanol. But it turns out methanol can be used even in the existing engines into your cars. You don't have to modify the car engines dramatically to be able to use directly methanol as your fuel. Therefore, you can imagine I'm using methanol into my engine, I'm running my car, and then in the process of using that fuel, I will be making carbon dioxide. I will be releasing carbon dioxide in the atmosphere. However, if I have a process of taking back the carbon dioxide and converting back into methanol, kind of looking at these two arrows, in my engine that uses methanol, I'll be burning methanol to carbon dioxide, the red arrow. But then if I have a chemical process to convert back carbon dioxide to methanol in this green, sort of following this green arrow, now I have a process which is going to be called carbon neutral. It's not carbon-free process, it's carbon neutral because you recycle the carbon source in this case. You're recycling the carbon dioxide to make methanol and then go back to carbon dioxide. This is another way how chemists could help addressing these energy problems. Okay, let me show you one last example that we're trying to address here. And this will actually be related to a fossil fuels which is being used today in various energy consuming processes. So this is taking advantage or trying to optimize the use of a fossil fuel. In this case, we're going to deal with a fossil fuel that's natural gas. The main component of natural gas is methane. This is sort of the simplest molecule that contains carbon. It's actually quite abundant on Earth. It's more abundant than oil or coal. Maybe almost as abundant as coal. However, it's a lot easier to exploit than coal. It's definitely way more abundant than oil. So it turns out that if we could use natural gas more efficiently, it could somewhat or address to some degree our energy problems. What is the problem with natural gas? Well, the problem is it's a gas. Okay? In order to be able to transport gas, you have to make it into a liquid. So you're going to compress it very high pressures of compressing gas into a liquid, and then you can transport that liquid to the appropriate location where you're going to use it. It turns out you have these huge ships which have these sort of big spheres here which are all liquid methane. Of course, this is quite dangerous, right? So it's quite difficult to transport natural gas. Let me tell you what actually people or oil companies are doing. It turns out that in an oil field, which has oil, you also have large amounts of natural gas. But it's much more cost effective to exploit oil, but not worry about natural gas. Actually, what they do, they flare it off. They burn it because they convert methane into carbon dioxide. And now I'm going to state something that's going to sound ironic. They are trying to protect the environment by flaring off methane into carbon dioxide. Okay? Why would they want to protect the environment by putting more and more CO2 in the atmosphere? Well, it turns out that methane, it's way more potent of a greenhouse gas. Okay? It's a really, really bad guy, worse than carbon dioxide. It's about 20 times more potent of a greenhouse gas. So indeed, by burning methane into carbon dioxide, they are protecting the environment. I would not call that the most efficient way of protecting the environment. How about try to take this methane, maybe convert it into something that's easier to transport? Maybe we could convert it into something that's a liquid, and then use that liquid, and maybe use it directly into our car engines, or maybe just later on convert it into something that's useful. So trying to be more efficient in taking advantage of this quite abundant fossil fuel energy source. And that's one example, or one other example, how we like to address such basic chemical problems, which are so important to these energy transformations. So in this case, what we like to do, and this will be the chemical structure of that gas, methane, found in natural gas, we like to actually put together several of these molecules of methane through various chemical reactions to make a longer chain. This will be called longer alkanes. You'll learn when you take general chemistry and organic chemistry if you haven't taken those courses yet. But this will allow us to now convert methane into a liquid chemical. It's almost similar to what gasoline is. Gasoline has about between 6 and 10 of these carbon centers all linked together in various ways. So this will be a very efficient way of converting natural gas at the point where it's being extracted on this oil field, and instead of flaring it off and just kind of not using it at all, trying to convert it into something that's useful and can be transported more easily and used maybe even directly as a liquid fuel. Okay? So I put here together all the three types of problems that we as chemists could address or could try to improve these chemical transformations, which are the basis of very important energy-related applications. We can try to use solar energy to convert water or to split water into oxygen and hydrogen, and use hydrogen as our carbon-free fuel. We could try to maybe convert natural gas or methane into a liquid fuel, which is easier to transport and easier to utilize and can be utilized actually than just burned off. But also we could try to take carbon dioxide, another greenhouse gas, and convert it into something that's useful, into a process that will lead to a carbon neutral overall type of a or recycling mechanism. You can burn your methanol into your gas engine, into your car engine, and then regenerate CO2, and doing this in a reversible fashion. Okay, so now I can finally go and address this kind of abbreviation I have above each one of those arrows. This CAT represents a catalyst. Okay, what is a catalyst? Well, I'm going to actually show you a small demo on the next slide and show you how a catalyst could help a reaction. I can do it more precisely by using this graph here. Some of you may have seen this. Some of you may say, okay, what is this? I see some humps here. I see a hill. I see 3 different smaller hills here. What are those? Well, the way you should think about chemical reactions in a very simple way. When you have molecules that maybe at different temperatures they're going to move fast or faster or very fast, okay, or very slow. Well, it turns out to have a reaction happen, you need to have those molecules interact with each other. So you need to have 2 molecules kind of interact with each other, kind of hit each other, and then a chemical reaction would occur. It's a quite complicated process. You need to force two molecules to come together. They usually want to avoid each other for different reasons, for different physical processes that go on in those molecules, or actually that make those molecules exist in the first place. So it turns out you can think about this very simply by just imagining that a catalyst, instead of having two molecules just hit each other and the reaction happen, just imagine that the catalyst is going to bring together, is going to talk to both molecules and kind of make them like each other and talk to both of them and eventually convince them that it's good to go and make the product. It's good to react. It's okay to react and make the right product. I know it's a very simple explanation, but pretty much what you end up doing, if this will be a hill that you have to go over, that is the process of getting those molecules to interact with each other, and they have to go pretty fast, and they have to interact in the right way to make the right product. Well, if you actually go slower and you talk to the catalyst, and the catalyst talks to both molecules, you're going to go over these smaller hills here, and there's going to be some discussion, and one molecule is not going to want to discuss with the other molecule and so on, but eventually you convince all of them to be friends and play well together. Okay? Well, let me show you how such a catalyst could help a process that maybe will not happen at all if you do not have a catalyst. So I'm actually going to use a YouTube video which shows a chemical demonstration called the Genie in the bottle.
Oh, great Genie.
Ooh, Mark wants 3 more wishes.
This Genie is so special, Mark, that you gotta put safety glasses on. It's not all in the Genie.
Fiery Genie.
No, just the Genie inside. So here, so watch this. Oh, great Genie, come out of the bottle. You can just see. Yeah, I know. Get out. I bring the prod. Oh, we have to uncap because it is a lazy Genie.
Oh.
So here's what great Genie. Let's see. Oh, great. Oh my gosh. Oh, great. Wow. Smells a lot like a Genie too. Ooh. Bottle's getting warm. Mark, viewers have said, I'm going to tell you the secret too quickly. So it is I set up one for you. There's a Genie inside. Right. There's not chemicals. So there's just a Genie inside there. So you open it up, and then I'm going to let you guess how it works.
Right.
Right. This one, oh, great Genie.
Oh, great Genie. Please exit the bottle. 130 million this weekend. Yeah. Nothing. No.
The Genie had to be rustled just a little bit.
No.
Yeah. Yeah.
Might be.
Oh.
There you go. There it is.
Isn't that very, very great? So a special effect artist, we use something like that. Honestly, the burning sensation in the lungs goes away after a while. So that's because of, yeah, Genie wants to take a shower. That's all right. So I'll give you a little secret. There's a chemical down inside. Any idea what that is?
It's obviously not nitrogen or
No, because it's warm. So
yeah.
and you'll be able to see it here in just a second. Take a look at this. It's sulfuric acid. No, it would be a little too dangerous. But it's not like this isn't dangerous. Mom used to use something like hydrogen peroxide.
Hydrogen peroxide.
Right. So it has 3%. So you go to the store and you get that, and it bubbles on your skin and easily releasing oxygen. This is 30%. So so you'd get burns on your skin if you even touch it. So you have to be very, very careful. But let me show you how we put the whole thing together. All right. So if you bring over a clear bottle, we'll show the viewers how we do it. So first of all, we're using 30% hydrogen peroxide, and we've got to release the oxygen from there. So we want that, and we're going to have a little bit of that steam or that vapor that's going to come off as well. So there's our 30%. And then the next part here is called a catalyst. And so if you look here on the table, it's a black color called manganese dioxide. And a catalyst is something that is not consumed in the reaction. It's just used to kind of speed along the reaction. So I will put some of that manganese dioxide here in this little piece of toilet paper, or tissue paper, right? So now this was hanging on the bottle like this. You didn't see it, and then there was a little cork that was here. I cut off the string. See? You got it. So as soon as you release the cork, that falls down inside, and you start to see the reaction. Isn't that just beautiful? And the little Genie comes out. So a lot of special effects, and today kids need to know something about that science isn't just a lab coat, the guy in the bow tie, and that whole thing. There really is something that happens in the movie.
Yes, this makes it so fun. And these are all things that you can a youngster can purchase and work with?
No, this is going to be a teacher's going to do something like this because of 30% hydrogen peroxide. Take a look at the bottle. Oh, wait, you've got a new suit. So look at this. You can actually see the bottle getting warm. This is just a regular soda bottle, but you can start to see how it shrank just a little bit there. That's because it got so hot. So it really is a nice exothermic reaction. I really think that's fun. I've never had one just take off that long before, so that's wonderful. Yeah. Well, you're going to get a new suit. People spot. Sorry.
Did you notice you had a hole in your sleeve? It's like, yeah, it's expanded. I got a hole in my sleeve.
That's why we never allowed to be together. Out in public. It's just, this is what we do. Hey, there's a lot of stuff up on the website. We've got almost 400 experiments. The Genie in the bottle is a hard one to read great, but it has some other things that use some hydrogen peroxide, which will start very well.
Okay, so hopefully you got to see what a catalyst can do to a reaction. Of course, this was meant to be more sort of funnier than my reaction I'm going to show in the next few slides, but it's the same concept. It's the same concept of how a catalyst would go. Just to make sure I show you the chemical reaction that occurred in that Genie in the bottle demo. We had hydrogen peroxide, as they mentioned in the video, and the hydrogen peroxide, in its normal state, it does not react very fast. It slowly decomposes to make water and dioxygen. This will be quite important in the next few slides. But this reaction by itself is very, very slow. That's because we had that big hill we have to go over in this chemical reaction. When we put a catalyst, in this case we had manganese dioxide, this is our catalyst, suddenly the reaction happens very, very fast. So you can see it happening in a few seconds, and this will lead to fast decomposition of hydrogen peroxide to give you water and dioxygen. This reaction is a very so-called exothermic reaction. It gives off heat, and that's why you could see the steam forming. So pretty much that was just steam forming because you almost boiled that water, and at the same time you make oxygen, which is a gas. So that gas evolves, just like your carbon dioxide into your soda, for example. So that's exactly what pretty much, if we want to put in this graph again, that's exactly what happened in that case. When you didn't have manganese dioxide, it's very, very slow to convert hydrogen peroxide into water. That's why you can store hydrogen peroxide in the bottle or in a beaker on a bench top for many, many days, many, many weeks. However, the moment you put manganese dioxide, this reaction happens within a few seconds, and you're left only with water, and then oxygen evolves very fast into the atmosphere. So that's the magic of catalysis. That's the magic of a catalyst. Some of those reactions I showed you on the previous slide, all of those reactions would not happen on their own. We have to help them to speed them up using catalysts or catalysis in general. The process is called catalysis or catalyzed reactions. That's exactly we as chemists are working on and trying to help these chemical transformations which are so relevant to these energy processes. So let me show you again one of these reactions. I'm just showing you this splitting of water into dioxygen or making dioxygen from water. It turns out that nature can do this process. Nature can oxidize water to dioxygen in a process called photosynthesis. If you're here last week, Professor Kermeyer has talked about photosynthesis, the whole process of photosynthesis. Well, one of the steps of the complicated process of photosynthesis is this water oxidation process, which occurs in photosynthetic organisms. The most common ones will be plants, right? In the green leaves, you have the process of photosynthesis occurring. There are a few other organisms that also can do this type of transformations. This is kind of the machinery that makes oxygen from water. Very, very complicated. These are biological molecules called proteins. And there are actually many of them to make this very complicated complex that can do this reaction. You see how simple the reaction is involving such small molecules, but you need all this machinery to do this kind of process. And just to connect the demo you saw on the previous slide with this biological process, it turns out the center where this reaction happens It's sort of buried inside this machinery. But what's important, it uses, and these spheres that are buried inside this complex, these spheres represent manganese ions. The same manganese ions you saw on the previous slide in that demo that catalyze the decomposition of hydrogen peroxide into oxygen, again, oxygen, and in that case also water. It's a slightly different type of a mechanism, but you could see how these ions, for example, manganese ions, and any other, some other types of ions, special ions like that, could catalyze these reactions. That's exactly what we're trying to do, at least in my research group. We're trying to use these special metal ions as potential catalysts for those chemical transformations I showed you on the previous slide. So how can we do that? Well, you can think sometimes of chemists as molecular engineers. What does that mean? We're trying to make small machines or small robots, which are actually just simple molecules that can help perform a chemical reaction. This is the chemical reaction, let's say, that we're interested in this particular project. So how can we try to do that? Well, let's think for a second. If we want to make this molecule dioxygen, even its name says dioxygen because it has 2 oxygen atoms. Well, in order to be able to do that, what you have to do, and again, think of them as just simple, maybe Lego pieces. Each molecule is a Lego piece, or it has 3 pieces, I guess. It has 2 hydrogens and 1 oxygen. And you have these 2 parts, these 2 molecules. You have to bring them together. You have to have the 2 oxygen atoms interact with each other to make this molecule. But at the same time, you have to get rid of the other pieces, which are your 4 in this case, because you have 2 molecules of water. So you have to kind of get rid of 4 hydrogen atoms in that case, or 4 protons, depending which charge you have on that atom. So that's kind of what we try to do from a molecular point of view. If we can build a catalyst, which is going to be a molecule that can maybe bring, and I know this is a very simple, again, description of how chemistry works, but if you have a molecule that can bring 2 water molecules together, kind of pluck off the hydrogen atoms, and then force the 2 oxygen atoms to come together, that's what with a catalyst for this process we'll have to do. That's why we call this sort of engineering at a molecular level. In a way, that's what chemistry is, especially in this kind of processes. I've showed here, and maybe this is a bit too complicated, but we want to take these metal ions. It could be manganese ions. It could be some other ions that we're working on. And those ions will bring the water molecules together. Maybe you're going to bridge, maybe it's going to bridge those molecules. Maybe we're going to have 1 water molecule kind of interacting with 2 different metal centers, and then remove the hydrogen atoms, and eventually get those naked oxygen atoms, and force them to interact with each other to give you the desired product. So again, this is kind of what I mean by molecular engineering in a way. So we try to make these complicated molecules. And again, you don't have to remember. I assure you, I'm not going to test you on these molecules. Okay? Just, we can look at them as very simple as this one right here. Think of it as having sort of this, what would that be? How would I think of it? Let's think of it as a lobster, which has arms, like the 2 claws. And the 2 claws are kind of the 2 sides of this molecule. You have some special atoms there, which will be important for our transformations. And this big molecule is going to bind to 2 metal centers, or these metal ions, these M notations here. And then this big thing is going to now go after a water molecule, or 2 water molecules, strip them of the hydrogen atoms, and then force those 2 oxygen atoms to react together to give you oxygen. That's one way in which we as chemists can design these molecules. Now, of course, there is quite a bit of design, and not the first molecule we make is going to be successful. Okay? Sometimes not even the 10th molecule we make is successful. Sometimes not even the 100th molecule we make is successful. But we're still trying hard to make such successful catalysts for these chemical transformations. Okay? So pretty much we would like to be able to have such molecules which keep doing this process. They keep taking 2 water molecules, they remove the hydrogen atoms, they make oxygen, and they release it. They go back, take 2 more water molecules, remove the hydrogen atoms, make oxygen, and then go back. That's in a way what a catalyst does. It does not get consumed in the reaction, and you heard that in the demo as well, in the video. It keeps doing the reaction many, many times. So that's why it's so efficient. You only have to make a small amount of this catalyst. It may be a complicated molecule, and it may take a long time to make it, it may be quite costly. But if it's an efficient catalyst, it's going to keep doing the reaction many, many times, such that overall it will be quite efficient to take, for example, water and make dioxygen, at the same time make those hydrogen atoms, which will end up making your hydrogen molecule, your fuel, that you can use in the fuel cell car. That's exactly what I show here. So these protons and these electrons end up making a hydrogen molecule into a slightly different type of a process. So this is just to show you what kind of molecules we make, and this is actually one of the molecules we have made. Now this metal ion, this ion we are using, is no longer manganese. It's another ion, which is called nickel. And this is what we made, and this indeed can take 2 water molecules, remove the hydrogen atoms, and we're happy to see that we can make dioxygen. We still have to work to improve this system. At this stage, this system cannot do this process many times. It's not really a catalyst. It can only do it once. So now we're working hard to try to do it many, many times to convert this molecule into a catalyst, into a molecule that can keep doing this reaction many, many times over. Okay? So this is sort of one way. And I want to make sure how are we doing on time. I guess Caitlin is not here. Okay. Maybe I'll just a couple more minutes and then maybe I'll stop and I'll take questions. Maybe it's easier to do that than show you how we can address the other problems. I'll stop after these two more slides. So that was one example of how we can develop a molecular machine, a molecule, a catalyst that could take, in that case, water molecules, bring them together and make dioxygen. Well, the same approach could be applied to the other 2 reactions I showed you on that introductory slide. Let me just show one more example. This reaction of taking methane and sort of removing one of these hydrogen atoms from methane. So methane has 1 carbon atom and 4 hydrogen atoms. So its chemical formula is going to be CH4. So if we could try to remove from 2 of those methane molecules a hydrogen atom, and then put together what's left after removal of those protons, you're going to make this molecule. This molecule is called ethane. But if you keep doing that, you're going to make this longer chain type of molecules, which now become liquid fuels. And that's exactly what we're trying to do. And again, in this process, we are using these molecular machines where we're trying to maybe bring together 2 methane molecules, remove 1 hydrogen atom from each methane, and then make those 2 groups, and these are called actually methyl groups, force those 2 groups to react with each other, to interact with each other, to make ethane. You can see it's somewhat similar to what we did when we dealt with the water molecule. However, now we have to actually use different types of metal ions and different types of ligands. But kind of a similar idea behind our design. So let me actually show you in this case how we do this. In this case, we use these flexible arms. We use these flexible robots or machines that can bind these metal ions. And I'm showing here some of these complicated molecules. Again, you don't have to remember their name. Okay, you can actually call these N4 because it's very simple to, don't remember this whole name. But let me show you how we could have something like that occurring. So in this case, you are using a different type of a metal ion. Here we are using palladium. Palladium is another one of these metal ions, which is quite efficient as catalyzing different types of reactions. So in this case, what we end up doing is we can take something that already has those groups. This Me stands for CH3. That's a way of how chemists simplify these notations. And pretty much what we have going on in this case, and these are sort of the pictures of how these molecules look like. When we react this molecule with dioxygen, we see a change in the geometry of this molecule, which helps this process to occur. So again, using these molecular machines in a way. And eventually, we make our desired product, having those 2 CH3 groups connected together, which is ethane. We make the ethane molecule. So you can see, again, an example where by using these molecules that can move and change their geometry and combine to different types of metal ions, we end up catalyzing, or ideally catalyzing, another type of reaction. But we still are dealing with very similar approaches. We're trying to pretty much, in the first example, take two water molecules, remove the hydrogen atoms completely, and have those oxygen atoms interact with each other to make oxygen. And at the same time, we're going to make hydrogen as our fuel. But in this case, we're trying to take methane, another molecule, actually take two of those, remove the hydrogen atoms from one hydrogen atom from those methane molecules, and then get them to interact together to make ethane. So even though those two reactions are completely different, and we have to use completely different types of these big molecules, and also use different types of metal ions, we are still using the same type of approaches. We're trying to design these catalysts that can help this chemical reaction occur. And these chemical reactions are very important to various energy processes. And that's exactly why I think that chemists in the near future will play a very important role in trying to address these energy problems by trying to develop these molecular machines, these catalysts, that can catalyze those reactions of interest, such as the one I've showed you in the past several slides. So I think I'll stop here, and I'll be happy to take any questions you have. Yes?
How's the energy density of H2 and O2 compared to that of gasoline, for example?
Right, that's a very good point. So it turns out hydrogen is quite dense in terms of energy density. It's quite dense. But you have to have it. So the big difference there is that hydrogen is normally found as a gas. Gasoline is normally found as a liquid. So in order to have, if you compare the energy density of liquid hydrogen to liquid gasoline, hydrogen is actually has quite high energy density. If you be to have gas, hydrogen gas, then of course the density will be much lower because now we're going to take a lot more volume. So that's why in these hydrogen fuel cell cars, you have to be able to compress hydrogen into a liquid form. And there's a huge interest in trying to develop various storage methods for hydrogen so that you can increase that energy density. But if we could do that, and there are ways of doing it, then it will be very competitive with using gasoline as your fuel. Very good question. Yes?
Is this endothermic reaction or an exothermic?
So it turns out yes, my bad. So the question is this reaction exothermic or endothermic? That is, does it make energy, or does it give off heat, or does it require energy, or does it require heat or sunlight? So I'm going to go back to the overall reaction we're trying to catalyze. Okay, this is the reaction itself. Here we have. It turns out taking methane and reacting with dioxygen, if you get that reaction to go, it's a very exothermic reaction. It gives off energy. Actually, if you let these two molecules react with each other, they very quickly react all the way to making carbon dioxide and water. That's actually the problem, trying to stop this process to some molecule like ethane. Because you can take methane, right? Methane is your natural gas. Your gas stove has methane. When you turn on the gas stove, so pretty much you use that spark to actually start turn on your gas. In that process, in your flame, you actually have exactly this reaction, except that you take methane plus oxygen and end up going all the way to carbon dioxide and water. So of course, you now want to do that in an oil field. That's exactly actually the reaction happening in these flames. It's exactly that. This is a huge gas stove, if you want to think of it that way. Of course, it's completely useless, but that's exactly the problem we are having. The problem we are having is actually try to stop after just one reaction only to make this molecule. And that's why you have to use very specialized types of catalysts to stop there. But the reaction itself is very exothermic. It was a very good point, because the other reaction I've showed you before, where you take water and you split into oxygen and hydrogen, that reaction is an endothermic reaction. It requires energy to happen. So in that case, that's where we use solar energy. In this case, we don't have to use any input of energy, but you have to stop it from going all the way to carbon dioxide and water. Very good point. Yes?
Well, if someone was going to come up with a system that would do this, what if it surpassed the energy level of oil and we quit digging for oil? What would be the source of methane then? Garbage, or would it be fracking?
That's an excellent point. So in the near future, one could use, for example, the natural gas that exists in these oil fields. Let's say we run out of oil fields, therefore, of course, we're going to run out of the corresponding natural gas. There's quite a bit or quite large resources of methane which are trapped with water in ice. So it turns out you have these methane hydrates, they're called. For example, in Canada, in Siberia, large quantities of methane, which are kind of trapped in those ice, in various forms of ice. Usually could be embedded in some maybe old oil fields, which actually, given the low temperatures in those locations, have converted into these so-called methane hydrates. So those actually, if people have started to exploit those, and that's exactly what I showed you that we could use natural gas for the next 1,000 of years. That's taking into account those particular resources, those particular locations where you have these methane hydrates. Let's say in the further future, you could imagine actually doing, like you said, like trying to convert or make methane from biomass. It turns out there are some organisms which can make methane. That's the way they operate. They make methane as a byproduct. So we could try to take advantage of that. And now, of course, we'll have to combine that with biology. Or we'll have to maybe modify some of those organisms genetically to make more methane in that process. But that will be one way of doing it. Another way of doing it could be potentially to try to, let's say, take carbon dioxide from the atmosphere and convert that. Instead of converting it to methanol, as I've shown you in that in one of the early slides, we could potentially try to convert it to methane. It's a bit more costly from the energetic point of view, but could be potentially used for that. Now, what I'm showing you here is sort of maybe a quicker, not necessarily a quick fix, but it's trying to help optimize the energy, or try to optimize the utilization with the currently existing energy source. In this case, it will be fossil fuels.
But what are the dangers of getting the energy out of the ice and things like that? Could that create a potential very dangerous situation, releasing it into the
That's an excellent point. So that's absolutely true. So for example, global warming, in a way, leads to melting more and more of these cold environments where you actually have these methane hydrates. So with time, that will happen. Methane is actually being released in the atmosphere as we speak. There are many of these organisms that just make methane, and that methane is being released into the atmosphere. And that causes a problem because methane itself is a very potent greenhouse gas. But in this case, for example, the way I imagine, if we have a catalyst that's efficient at this transformation, if we could use it in an oil field to just convert that methane that's now normally flared off to make a liquid fuel, then that's much more easy to transport. You can use the current infrastructure transporting oil. And that will give you some additional efficiency of using those fossil fuels resources.
I actually have a question online here. Oh, shoot, I lost it. It just canceled me out. I think the question was asking, no, I'm going to use your microphone. Wanted to know if there were any ways, are you aware of any mechanisms to make hydrogen safer to use in a hydrogen-based car where high-speed collisions must be considered?
That's an excellent point, and that's maybe one disadvantage of using hydrogen as a fuel. So you have to compress hydrogen to now have a liquid or have high enough density of energy so that you can store more hydrogen and you can go further distances. Well, that's definitely a potential problem. On the other hand, if you have efficient storage of hydrogen and it's a safe way of storing these high-pressure hydrogen. That's one way of addressing a potential or trying to avoid very catastrophic collisions. At the same time, people are working on other ways of storing hydrogen, not only to store it as a liquefied gas, but developing some special materials, special solid-state materials, where you can actually have hydrogen interacting in a molecular fashion with some special materials, such that you don't just pressurize hydrogen, but hydrogen undergoes a chemical reaction and binds, for example, to a specific type of a solid state material. And by doing that, it turns out you can put quite a bit of hydrogen and store it. However, you're going to store it in something that looks like a solid material. It's almost like imagine having a piece of some porous material, like a sponge, let's say. And you pass through it hydrogen gas, and if some of the hydrogen molecules are going to bind in a chemical fashion, it's going to make chemical bonds with that sponge. So by doing that, you're going to increase the mass of that sponge, and that mass will be only due to the hydrogen you bind to that sponge. So that's one way of storing hydrogen in such a hydrogen fuel cell car. So not necessarily just by increasing the pressure of gaseous hydrogen and convert it to liquid hydrogen. That's one way of trying to address that problem. That's more of an engineering problem, along with some of these material science problems where you're trying to develop better and better sponges for hydrogen storage.
Okay, well, if there are no more questions, let's go ahead and thank our speaker.